Okay, tic-tac-beta. Next few questions are about a game called tic-tac-beta. Tic-tac-beta is similar to tic-tac-alpha, but there's several twists. Your marker starts in a random square, but the goal is still always in the bottom right corner. You can move your marker to a square that is previously occupied. You may not move your marker. I'll keep track of occupied squares in my example below by coloring them blue. It's no longer just to keep playing until you win game. The game always ends after a maximum of 8 moves, and your score is as follows. You get 10 points if you get to the goal. You lose a point for every move that you make, so you can have a negative score. And yes, your max possible score does vary depending on where your marker starts. Okay, so important note, depending on your screen size, you may need to scroll right. Fine. So here's an example. So I go down and right, and I win. And the score is 10 for getting to the goal, minus 1, 2, 3 moves. So that's how, okay, that makes sense. This takes a little bit longer, so they go up, left, down, down, right, right. So that should be 10. And then they made 1, 2, 3, 4, 5, 6 moves. So 10 minus 6 is 4. Good. And here's the dumb play, right? So they go 1, right, down, down, left, up, and they're stuck, and they get a score of, they moved 1, 2, 3, 4, 5, negative 5. All right. So how large is the state space for the tic-tac-beta game? How many states do you need to fully represent tic-tac-beta as a state space search problem? Justify your answer. So again, we need to figure out what is it that I need to keep track of. And obviously, we still need to know what room the player is in, right? And there's 9 possibilities for that. But now it gets more complicated because, you know, suppose the player is in this room. Each of the spaces around the player could actually be colored in blue, or they could be white. I mean, we could get very specific about what is possible for a given configuration, but let's just talk sort of about the big O of the state space. So that would be, well, let's see. I mean, we could have a situation where all of the squares are blue, maybe. Let's imagine that, right? But we could also have the situation where the smiley is here and this space is white, but all the other ones are blue. Right? Or we could have the same situation where, you know, maybe this one is actually blue, but this one's white and the rest are blue, right? So there's all these different possible ways to lay this out. And so really, what do we need to know for a given state? We need to know which room is the smiley face in. That's our nine possibilities, right? But we need to multiply that by however many sort of extra opportunities there are. You know, however many of these we need to draw for every single situation where the smiley is in any particular space. So if the smiley is in, say, this space, then really what we need to think about is all of the cases where this room is blue or white, this room is blue or white, this room is right. Each of these is 2 cases, right? So there's, you know, if the smiley is in room 2, then we've got room 1, room 3, 4, 5, 6, 7, 8, 9, right? Then room 1 has 2 possibilities, right? It could be blue or white. And room 2 has 2, oh no, so room 2, the smiley's in there, sorry. Room 3 could be blue or white. Room 4 could be blue or white. And we need to be able to do a board for each of those to represent each state, right? So for the case where the smiley's in space 2, there's how many? This is 2 times 2 times. How many of these are there? There's going to be 8 of these, right? 8 other rooms that it could be black or white, or black, or sorry, blue or white. And if we have 8 2's multiplied together, that's the same as 2 to the 8th, right? So for each of the 9 positions where the smiley face might be, there are 2 to the 8th options about how the rest of the rooms could be organized, could be colored, right? Are they blue? Are they white? Are they blue? Are they white? Are they white? So my final answer for this, for this problem is going to be 9 times 2 to the 8th. Now, if you looked at the problem a little bit differently and just said, well, each room could be a smiley face, or it could be blue, or it could be white, right? And you sort of forget about the fact that there's only one smiley face on a given board, then you could argue, and I would give you sort of a lot of credit for this, that there's actually 3 possibilities for each of these squares, right? And so you multiply all those 3 different possibilities together, and you get 3 to the 9th power. So I think given that there's really, we know you can only have one smiley in here, right? And that's a pretty general requirement. This is probably a better answer. But saying that the state space is 3 to the 9th, that's reasonable too, because even with this answer, there are a bunch of configurations that you couldn't have, right? So for example, we're going to have states that represent things like the board where, let me just draw it in this sort of little corner here. If you have the smiley here, and all the ones bordering the smiley are white, but just these guys are blue, that's not really a possible state that we could go to, right? But in our graph, it's just going to be a node that there are no in arrows to, right? That you can never end up at this state. And so not all of the 9 times 2 to the 8th states are legitimate states. And so as long as you explain to me how you came up with the 9 times 2 to the 8th, I'm pretty happy. And similarly, as long as you explain to me how you came up with that 3 to the 9th, I'm also pretty happy. Oh yeah, what about the question in the score? The problem talks about a score. Well, for the purposes of figuring out the state space, we don't even care, right? The score will affect the cost of different transitions, and it may, in our state space, right, it might be that you lose a point, so you have a -1 on a particular arc. But for the purpose of figuring out how many states there are, we don't care about the score.